to the first meeting of the spring. If you don't believe it's the spring, just wait a few weeks. It's very difficult. Over the past few weeks, it has been less than freezing and outdoors, but hopefully very soon it will get more comfortable. There are lots of exciting things going on. There was actually, I don't know if all of you are aware, but there was a paper yesterday in Nature about the analysis of the material from the Bennu asteroid, and they found the amino acids and the ingredients that seem to, and actually they found also the amino acids with both chiralities, with equal probability. All life forms on Earth have one chirality, so it's clear that the choice of chirality was made on the planet, not from the early primitive material that made the solar system. And so these are very interesting indications that life may be pervasive. If you find it on an asteroid, if you find the ingredients for life on an asteroid, very likely that they exist also in the liquid ocean under the ice on Enceladus or Europa. So that's very exciting, a new development as of yesterday. So just check out the paper. And we also heard an excellent colloquium by Glenn Starkman, and who was trying to convince us, and actually that's true, that is a very important insight, that perhaps the universe is not isotropic. And many of the theorists that listened to Glenn could not imagine a simple model that would explain that. So Glenn will give us the model very soon. He will be the first speaker coming from Case Western, and actually I know Glenn from when he was a postdoc. We collaborated on a paper. And he will talk us about whether we can hear the shape of the universe. And then we'll hear from Tiger Lu from Yale. Where is Tiger? Over there. Who will tell us about the Super-Puff HIP-41378f. That may be a ringed planet. We will put dynamical constraints on that. And then we'll hear from Charlie Mpetha, over there, from the University of Edinburgh, who will tell us about the infall region of galaxy clusters as a complementary probe to cluster abundance, a probe of cosmology, I guess. And finally, we'll hear from another tiger, a tiger Hsiao, over there, from Harvard and Johns Hopkins University, and he will tell us about the first star clusters observed in the early universe with JWST and gravitational lensing, which is very exciting. But lensing allows us to see clusters of stars. Yeah. Okay, let's start with Glenn. Oh, and Glenn, one question that was asked by someone who cannot attend. Maybe you can just comment on that. And that's Gary Melnick. He is unable to attend your presentation, but he was asking whether, and maybe you can touch on that, whether there are any signatures in the non-Gaussianity, FNL, because that's something that Sphere X is going to measure.
So I'll start with, that's a great question. The answer is you have to be really careful in the statistically isotropic universe of how you calculate FNL, because your estimators all assume statistical isotropy. So Gary and I should talk. Ah, right. Okay. Okay, so I was tempted to talk about something completely different. I was tempted to ask all of you what the speed of light and the speed of gravity is, and I know what your answer would be, I'm pretty sure, and then to point out that that's actually the speed limit in a vacuum and not the speed, but we'll talk about that some other time. So I wanted to talk about something that flows from the colloquium. Can we hear the shape of the universe? And this is work that I do with this fantastic collaboration all around the world. You can look at the students, the postdocs, the faculty, and tell us that you want to join in, because there's lots of great stuff to do. And just to recap quickly, what I did is pull 4 of the representative anomaly statistics, statistics about the large angle anomalies of the CMB, and point out that they're actually only very weakly correlated with one another. That their combined p-value is somewhere around a few times 10 to the minus 8, with a systematic error between, of that order. And so statistical isotropy, even just from these four, and there are many more, with something that I call the alternative to look elsewhere penalties, which is look more closely rewards, telling us that the evidence is at least 5 sigma just in TT correlations. So the question is, if you learn that the universe is not statistically isotropic, what do you do? Because our theory tells us it should be. Well, the first thing you can do is you can find a fundamental physics model, and that's going to be the thing I'm going to talk about most. But before I get there, I want to point out there's two other things you can do. You can try to make reasonable phenomenological extrapolations and test them. And you can also continue to test this idea that it's what we call the fluke hypothesis, that is just bad luck in lambda CDM. And which means, yeah, you assume lambda CDM is right, and you predict how the measured anomalies would affect other observables and test those predictions, which, by the way, is a frequentist approach, unashamedly. Or you say, okay, if I have these anomalies, then there's some explanation. What would I expect a physics explanation to tell me about other things? So, and those two really go hand in hand. So let me give you an example. One of the things we learn is that the variance of the northern sky in CMB temperature is low. Okay, so here it is. Here is the probability distribution function for the variance. This is what it is in the south, this vertical line sitting right there at the peak of the distribution. This is what it is at the north with a p-value of like 0.1%. And you might think, oh, well, low variance in temperature over a large region of the sky probably means low variance in the underlying scalar fluctuations, which probably means low variance in the E-mode polarization, then that's same region. Lambda CDM says, nah, you don't get much of an effect. You get a slight shift in both north and south if you have low northern T. And so if we saw that we had a reduction in the polarization variance in the north in E, then that would be a test of the fluke hypothesis and of the of this phenomenological expectation. So here is what we'd expect. We'd expect the variance to be right here. And if we sat 10% outside this, which is what we do in T, you can see that that would be way outside, outside these isoprobability contours with very low p-value. Okay. So that's something we could do. We could also look at the absence of large angle correlations. So in the temperature, we see that there's essentially no correlations in temperature above about 60 degrees. And we can say, oh, well, the same thing's going to happen in E. After all, this is due to underlying curvature fluctuations. And here, by the way, guess what? We predicted this distribution as what we should get. And you go out and measure it, and guess what? It is highly anomalous. Not at all what you'd expect in lambda CDM. This is what you'd expect in lambda CDM. It doesn't shift much, and instead you see this EE suppression. Okay. So to answer, partly to answer Avi's question, but really it extends beyond this, there are consequences of breaking statistical isotropy. It stops protecting things. Symmetries protect things in your theory, and they stop being protected. So in particular, in lambda CDM, the expectation value of any pair of ALMs is chosen at random is 0, okay? Except for the very special ones that are actually the same degree of freedom. Okay? And that people think that for example, the expectation value of any E and any B ALMs are 0, or T and B. They're 0 because, and people think this is due to parity invariance. It's not. It's almost all due to statistical anisotropy. So if you're anisotropic, you have a completely general covariance matrix. Okay? If you have parity conservation in addition, half of these go away. But the statistical anisotropy that we see actually is tied to statistical inhomogeneity, so we expect parity violation. Okay? And so we actually expect non-zero entries everywhere in this matrix, which is almost all of which are 0 in lambda CDM. All right, so I'm going to skip this because I want to talk mostly about the last thing, or the first thing that you really want to do is have new models that explain this. So here is the list of fundamental physical models I know of that break isotropy and are already in our theory. That's the list. Because non-trivial topology to the universe is just a statement that you were using the wrong boundary conditions for GR. Right? There's a statement that if anyone here has used periodic boxes to do their simulations, that those could be real. That the universe really could be a periodic box instead of an infinite E3, S3, or H3. Okay? So we can have loops around the cosmos. I should have brought a piece of paper. I actually did somewhere. And if you take a flat piece of paper and draw a triangle, and the sum of the angles on that is very good. Now you wrap it up and you make a cylinder, and the sum of the angles on the triangle are still 180 degrees. You didn't do anything. It looks curved because you're looking from the outside. But if you were living in that piece of paper, it'd still be 180 degrees. So a flat universe doesn't have to have trivial boundary conditions where it goes on forever. It could be like a cylinder where you can go around in one direction. It can be like a torus where you can go in two directions. That's in 2 dimensions. In 3 dimensions, the same thing works. Okay? So you can have a periodic box with opposite faces identified, and that is a flat Euclidean space. It's called the simple 3 torus, often called E1. It's called E1 because there's more than one possibility. I'll talk about that in a minute. This is not a new idea. Here's some people who thought about it. Schwarzschild, before there's GR. De Sitter, about the day after Einstein wrote down the S3 universe, he said that was the wrong thing to do. These people, Friedman, Lemaitre, you've heard of them. This is not the Witten you think. It's his father, et cetera, et cetera. So this is an old idea that maybe we have a better chance of going after now. So this idea, as I said, works in 3 space dimensions. It turns out there's actually 17 non-trivial topologies of Euclidean space. Here's the one we're used to, the regular periodic box. But who says that when you identify the front face and the back face that you couldn't turn it? Here it is turning it by 90 degrees, or 60, or 180 degrees, or 60 degrees, or 120 degrees. And here's this very complicated thing called the Hunch-Vent space, where you turn all the faces by 90 degrees. All sorts of interesting spaces, 17 of them, and guess what? They all have real parameters as well, so there's a lot of possibilities. And you should ask, why did we think we just lived in the one that I didn't show here, which is number E18, that is called the covering space, which is simple. Okay. So here are those 18. You'll notice that some of them have no compact dimensions. That's the one we've always assumed we live in. You can have 1, you can have 2 compact dimensions, you can have 3 compact dimensions. Only one of those preserves statistical isotropy. The others don't. They all break statistical isotropy. In other words, if you're in them, you can tell the difference between different directions. The universe is anisotropic. Okay? It turns out that almost none of them are homogeneous. They break statistical homogeneity. Okay? Some of them are orientable, which means you have a well-defined sense of clockwise and counterclockwise, and some of them are not. And we may or may not be allowed to live in those, but I'm not going to worry about those. Now, of course, space may not be flat. So we don't have to live in the analog of the flat plane. We could live in a curved space. Here is a spherical topology, a topology that admits a geometry of S3, but isn't the whole 3-sphere. Okay? In fact, if you ask, what do I mean by spherical topology? Well, there's a conjecture by Thurston proved in 2003, and that's it. I'm all done, and you'll have to ask me more later. But the point is that we can hope to ask the same question that Mark Katz did. Can you hear the shape of a drum? Who here thinks you can hear the shape of a drum? In other words, if someone played a drum outside and you had really good microphones, could you hear its shape? Anyone think you could? Okay, the people who think you can, you're physicists. The people who think you can't may be mathematicians. Because it turns out that there are drums that you can't tell the difference, but who cares? They're rare. There's pairs of them. For physicists, you can. And our real question is, can we hear the shape of a 3D cavity with imperfect ears? And the answer is, we think so, because it introduces, just like for the drum, it introduces all sorts of non-trivial correlations. And I should stop so that the next person can go ahead.
There will be some questions, but so there are observers in this room, and so suppose someone uses the Webb telescopes, finds a quasar or a high redshift galaxy. Where do you expect the copies to appear so they can go and use the Webb telescope to find those copies?
So the bad thing is that if you had asked me that question in, let's see, 2000, I would have said that there's a possibility that we would find such copies. Okay. Turns out that using the WMAP data and then the Planck data, what we can show is that the shortest closed curve around the universe that goes through us has to be at least 98.5% of the diameter of the last scattering surface. And that means we're not likely to see actual copies. And so it becomes that idea that we can look for what we call clones, topological clones, becomes a probably not viable approach to looking for topology. We really have to think of this as listening for the shape of the universe. In other words, the universe, everything we see is the imprints of acoustic modes that were in the universe in the early universe, whether it's CMB or large-scale structure. And we have to look at how the wave vectors that have been excited there, the Fourier modes that have been excited, and how they are correlated with one another in unexpected ways, which would be a smoking gun of topology.
So in your classification of the class 3 torus, you have 17 of them. How many?
Right, 17.
So just remind me, how about the 2 torus? I want to know your way of classifying this.
Oh, so
torus will be Klein-Bartel and
right. So that 17 included the Klein spaces. Okay. So it included the non-orientable spaces and the orientable spaces. Okay.
2 torus, how many?
And then
3 dimensions.
I think it's 2.
Just 2.
I actually don't know as much about two
So I have a
manifolds.
comment. Actually, there are more because, including the fermions, like in the standard model, we do have fermions, lepton quarks.
Mm-hmm.
They could give a periodic and anti-periodic boundary condition when you go through cycles. So they're actually more.
Right. So So there's.
Yeah, there's more, but I mean, certainly.
I'm happy to talk and learn a bit more. There's also more when you start thinking about possibilities of boundaries or defects. These are all the 3 manifolds, right? But there's a much larger set of things that aren't quite 3 manifolds.
So torus has spin manifold, and there's a choice of a spin structure as well. Just
right.
Fermions can be on the top, so there are more choices.
Right. There's more choices than just the geometry. There's also the field theory.
Yeah.
Glenn, you mentioned 98% of the last scattering surface, but doesn't it make the present time special? Because if we were to live, 1 billion years after the Big Bang, we wouldn't see that big of a volume.
Yeah. So you might ask, well, isn't it very unlikely that if it's already bigger than 98.5% of the diameter of the last scattering surface, that it won't be 100 times bigger or 1,000 times bigger? And the answer is, a priori, you would say yes. Now, the thing is that what one can show is that if the diameter of the if the shortest curve through us is bigger than about 1.2 times the diameter of the last scattering surface, then there would be no information about topology in the temperature. And so you say, well, that must mean this is going to be very hard. But actually, it means that if statistical isotropy violation due to topology is the explanation of anomalies, then the diameter the shortest closed curve has to be smaller than 1.2. So it's telling us that the fact that we saw anomalies is the same coincidence, would be the same coincidence, because those anomalies will also go away if, wouldn't be there at different times. So we happen to live at the time when those anomalies are low L, right? And that would be the same coincidence. Or, but if a topology is not the explanation of the anomalies, then yes, then it's very unlikely we'll see it.
Okay, let's thank Glenn again.
Can everyone hear me? Cool. Yeah, it's great to be here at the CFA. And yeah, I'm Tiger from Yale University, and today I'm hoping to talk about this fascinating planet in the HIP 41378 system that happens to be an extremely puffy planet on a cold orbit. And I'm hoping to explain how the dynamics of such planetary systems might not seem immediately connected to physical characteristics such as this, but it turns out can actually have a very profound role. So super-puffs are this fascinating class of planet that have emerged in the past couple years. And essentially, they're just these anomalously low-density planets of around 0.1 grams per centimeter cubed. So you can think of them as like giant cotton candy balls floating through space, right? And these planets don't really fit in neatly into classic planet formation theory because you need too much gas to form them. The gas to core mass ratio just doesn't really make sense in standard models of planet formation. Now, I don't want to claim that these super-puffs are some unsolved mystery because there are ways to form them, right? For example, tidal heating. If you have a planet very close into its host star, tidal heating injects a source of luminosity into the core envelope boundary, which puffs up the envelope, and you get a puffy planet. But all of these mechanisms rely on either the planet being very close to its host star or very young. And for the most part, this worked out, right? So I've plotted a few of my favorite super-puff systems in semi-major axis space, as well as the solar system, just for reference. And indeed, most of these super-puff planets are pretty close to their host stars, and possibly pretty young. That is until 2019, when the HIP 41378 system was discovered. And I'm not going to say the telephone number after this. I'm just going to call it the HIP system. But you'll see that the super-puff in question here is beyond the orbit of Earth. It's on a 542-day orbit. So none of the accepted mechanisms for forming these puffy planets really make sense anymore. So I'm here today to present this alternate hypothesis. And that's this planet's not actually puffy. Because if you think about how planetary scientists measure the radius of a planet, we use the transit method, and we just look at how much light is being blocked from a host star as the planet passes in front of it. And you'd imagine that you can block a lot of light from a puffy planet, but you can also block a lot of light from a normal planet that has an opaque ring system around it. Now, we're not even close to the first people to come up with this idea. This idea has been bounced around the community for a couple years now. But what we add to the puzzle kind of comes from the fact that the work I'm about to present is just as HIP-F is a ringed planet masquerading as a puffy planet. This work is kind of a planetary's obliquity paper and a dynamics paper masquerading as a rings paper. Why is that? Well, why do we care about the planetary obliquity? We care about the obliquity because you actually need the obliquity to see rings. If you consider the geometry of a transiting planet, if the planet has to pass in between us and the star, kind of by definition, the planet's orbit normal has to point perpendicular. And if you assume that a ring system is coupled to the equator of the planet, if the spin axis points in the same direction, we just see the rings face on. They're too thin, right? They contribute nothing to the transit depth. You need some sort of planetary obliquity to warp the rings out of the plane of the sky for it to actually block any light. So let's look at the system, right? I'm going to throw some numbers up on the screen here. But the important and maybe the most intriguing thing about this system is A, it's very compact, right? And B, there's a series of mean motion resonances in this system. So planets B and C are in a 2-to-1. And most importantly, D, E, and F are in a 3-planet compact resonant chain. Why do we care about that? Well, first of all, it turns out these compact systems are generally dynamically very unstable. What we've done is we first took the naive observational posteriors and integrated a an ensemble of 1,000 of them. And we plotted the time it took for the system to go dynamically unstable. You see time on the x-axis here, and you see by 10 million years, this system is overwhelmingly unstable. And this is a problem, right? Because the system is 3 gigayears old. So it's very unlikely that we're just happening to catch this planet in the brief phase of time that it's stable. But there is a solution, and the solution comes in the form of these mean motion resonances. Because it turns out, if your planets are in a resonant chain, this introduces these tiny islands of stability in your parameter space. Now, these islands of stability are a tiny fraction of the overall possible parameter space given by the observational posteriors. But it turns out there's a process that can preferentially bring you into these islands of stability. And that process is migration, driven by something like, for example, interaction with the circumplanetary disk. This is a method that has been used quite often in the past to stabilize these long, compact resonant chains, such as TRAPPIST-1, for example. And we did the same thing. And when we migrate our planets into resonance, they are overwhelmingly caught into these islands of stability, and you see the system is stabilized. So I would argue the fact that we even see the system today, given its long age, is kind of a smoking gun, right? That migration happened here. Well, that's all well and good, right? Why do we care that migration happened in this system? Migration is important because migration and mean motion resonances is kind of a smoking gun itself for the excitation of planetary obliquities. So this has been, this has been analyzed by a few authors, but this is a great paper by Sarah Milholland and Greg Laughlin, my advisor, in 2019, who showed that in many multiplanetary systems, it's very likely that if you have convergent migration, you can excite and maintain a high planetary obliquity. And this should happen quite often. And this happens through a process called secular spin-orbit resonance, which I don't have time to get deep into the details right now, but I'll give a quick overview. So like any resonance, spin-orbit resonance happens if you have a matching between two frequencies. There's the frequency associated with the recession of the planetary orbit, and there's the frequency associated with the precession of the planet's spin. Now, the first frequency depends only on the architecture of the system. This is well constrained from orbital data, so we know this pretty well. The second frequency, the spin precession frequency, depends on the physical structure of the planet. This is completely unknown, right? Especially considering we're arguing that we don't even know the planet's radius. So instead, what we did here is we first numerically calculated the first frequencies, the ones associated with the planet's orbit, using the orbital data we had. That's plotted here in the black dots. And the system's motion is quite complex, so there's actually multiple frequencies you have to match. We then took a range of physically reasonable spin precession values, which we denote with alpha, and we see if there's a near match with any of them. Now, we ran about 1,000 simulations varying this alpha parameter. One of the most important parameters, one of the most important dependencies to this spin precession rate is the ablateness of the planet, J2. So we plot in terms of that. And we see that for quite a few of these systems, for an ablateness a little bit higher than Saturn's, for example, you can excite the obliquity to pretty high values, more than enough to reproduce the transit profile. I'm just going to show you one of our simulations here in detail. You see all 3 planets migrating inwards until they're caught into their present-day values. And what I want to emphasize here is that the obliquity evolution of the planet, you're looking at a polar view of the planet with its spin axis here. This is caught into a very, very distinctive Cassini state resonance, right? And this is to show that this is not some random kick of the obliquity. This is a robust secular process that is expected to happen given the parameters we chose. Now, some of you might be thinking, a Saturn-like ablateness is pretty high, right? That's the most ablate planet in the solar system. And that's true. But what we care about here is effective spin precession rate, not the ablateness per se. And it turns out it's quite easy to enhance the spin precession rate. For example, with a moon greatly enhances the precession rate of your planet. And what this plot is showing is if you just insert any of the major solar system moons around this hypothetical planet, that provides more than enough spin precession rate to still capture you into the resonance. So you can get caught into the resonance with a relatively ablate planet, and you can also get caught into the resonance with a relatively unablate planet with a fairly reasonable moon around it. So that's it for the HIP-F system, but this is actually a pretty interesting result that we just kind of threw into the conclusions that I'm interested in following up on. We very briefly did a very similar frequency analysis for some of the other Super-Puff systems out there. And what we found is that quite a few of these other Super-Puff systems, which are multi-planet systems, are also very reasonably in the spin-orbit resonance as well, which of course also points to high obliquity. Now, I'll wrap up real soon. A lot of these planets are too close in for the ring hypothesis to really hold any water. So I don't think they're rings. But since they're close in, now we're thinking maybe there's obliquity ties involved. Maybe there's other sorts of ties. So this is an interesting avenue to explore that I'm very interested in right now. So yeah, thank you for your attention. I hope I've convinced you that something like these kind of physical parameters that you might not immediately associate with the dynamical history of the system. In fact, it is important to consider the dynamics of these systems, and they can have really profound effects in unexpected ways. So yeah, thank you.
So, like, the object that is doing the occultation is most likely an ellipse rather than a circle, right? So that would mean that ingress and egress would look different. And
glad you asked that. Yeah, this is so. Yeah, I'm not an observer, so this was by no means the focus of the paper. But yeah, this is how you would differentiate a ringed planet versus just a puffy planet, right? Because although they have the same projected area, the shape is different. So as you pass across the star, the signal in your transit is going to be slightly different in transit ingress and transit egress. And what we showed in a very back of the envelope way is that James Webb should have more than enough precision to see this.
But nobody checked.
Sorry?
Nobody checked. Yeah. It was not checked yet.
I believe I'm not sure if JWST has observed this yet. I know there are several proposals in for this planet at the moment.
Any comments, questions? Oh, please.
Hi. Thanks for this. I was also thinking about JWST data, but from the transit spectroscopy standpoint. What might we learn from the expected transit spectroscopy signal if it were just a planet with no ring versus something that has a ring?
Yeah, this is not my area of expertise, so I can't tell you why. But my understanding is if you have rings around a planet, you expect a featureless transmission spectrum. Again, I can't tell you why. Unfortunately, it's a little bit difficult to differentiate it this way because another popular hypothesis for these superpuffs is atmospheric hazes, which I believe also you expect a featureless transmission spectra. So it seems like it's not the easiest differentiation there, but I would think a featureless transmission spectra should be some compelling evidence at least for a ring system.
Any other comments, Ramesh?
So right at the end, you said maybe some of the other super puffs may also similarly be rings. But you also said that those are generally close to the parent star.
Yes.
So these are not icy rings then, because that will get sublimated in very short time. So what are you thinking of? Are these dust?
To clarify, I actually absolutely do not think any of these are rings. They are too close in, and the reason they're almost certainly not rings is because once you get too close to the host star, right, the rings are truncated much closer, and they're not necessarily always warped into your spin axis plane. There's this competing torque from the host star that drags some of the rings back down to the orbital plane. So the transit signature you get from the rings is much, much weaker. So actually, I think it's very unlikely that any of these are rings, honestly. But I think what they could be is, what this plot is showing is not that they are likely to have rings, but that they're likely to have planetary obliquity. And I think maybe the most likely outcome here is obliquity tides.
Okay, yeah, fine. Now your favorite candidate, is that likely to have an IC ring, or is it some other composition?
HIP-F?
Yeah,
I-
HIP guy.
I think the equilibrium temperature of this planet is 293 Kelvin, if I remember off the top of my head. But that's, it's unclear, right? That's assuming like a fully reflective surface. So it seems to be right on the edge of if icy rings
Well,
or.
it's room temperature. It's exactly 20 degrees Celsius.
Wait, okay, I'm misremembering that then, because it's definitely not room
We
temperature.
know that ice cannot survive at room temperature.
Yeah. I seem to remember that it's kind of right in that transition where either is possible. But for us, you can the extent of the ring is dictated by in large part by the density of the particles in the ring, right? And what we showed is that a ring extent large enough to reproduce the transit can be reproduced by both, in some cases, an icy ring or a porous rocky ring.
Okay, let's thank Tiger.
It's an alien artifact. Well, before he built the Dyson Sphere, he has
On the way to this.
on the way to Dyson.
Okay, can everyone hear me okay? So I'm a final. I'm a final year graduate student at the University of Edinburgh. I'm excited to tell you about this work that I've been working on in Waterloo in Canada for the past year. And it's got quite a long title, but I'll make sure to introduce these terms one by one. Very broadly speaking, it's on how we can use the infall region of galaxy clusters as a complementary probe of cosmology to other existing methods. So it's first just some broad motivation. Galaxy clusters, as I'm sure you know, are large collections of galaxies, typically hundreds of thousands, and they contain a large dark matter halo. So I might interchangeably use the term dark matter halo or galaxy cluster, just so you know that's what I'm referring to. There's lots of current motivation for observing these systems in various wavelengths. So at the top, we see a recent image from Euclid of the Perseus galaxy cluster in optical and infrared imaging. And then on the bottom, you see this beautiful all-sky survey from Erisita in X-ray, and you also see the Perseus cluster down here in the bottom left. And so there's a lot of motivation in multi-wavelength approaches to studying these systems, and it's kind of pertinent to investigate all the ways that we can use information of galaxy clusters to understand properties of the universe. So the two parameters of interest that I'll focus on is the amount of matter contained in the universe, which is given this parameter omega m, the density fraction, or how clustered matter is in the universe, which we can parameterize with this sigma 8 parameter. And so one really nice, easy way of using galaxy clusters to probe these parameters is by looking at your 3D survey volume, counting how many clusters do we observe, and then comparing that to simulations that have been generated with different choices of omega m and sigma 8. And then that gives you a preferential value for these parameters. So this was performed recently by Erisita. And this orange contour shows the 1 and 2 sigma constraints on omega m and sigma 8. So these are the best current constraints on these parameters from cluster abundance studies. And we see these constraints are great. They're starting to reach the precision of Planck. But there's this large degeneracy between these two parameters. And so we could combine the orange and the blue contours to improve our constraints. But the problem with this is Planck and cluster abundances probe very different scales and very different redshifts. And there's been recent hints of tensions between data sets which look at different scales and redshifts. So maybe we don't want to just combine these two. Ideally, we would have some method of breaking this degeneracy which only uses cluster information or cluster properties. And so that's the broad motivation for this work. As you'll see, the infall region provides such a complementary test. So what is the infall region? So here we see the density profile for a stacked set of dark matter halos in a cosmological simulation. The reason we stack many dark matter halos is if we look at the structure of a single halo, it's going to have some complicated asymmetric 3D shape, but we want to study the average properties of halos. So when we stack, we have this nice, smooth, isotropic profile, because all of the asymmetries will average out. So I've split this density profile into 3 different regimes. On the left is the inner profile. This is typically what you might think of as an NFW profile, for example. And this describes the virialized region, where material is gravitationally bound to the dark matter halo and is orbiting around the center. Furthest to the right, you have the environment. This just describes the field, where material is not interacting with the dark matter halo. But then there's this in-between region called the infall region, which is where material is being drawn in from the environment. It's infalling to the halo. It's very turbulent, and it's not necessarily dynamically relaxed. And this also is very highly dependent on the environment in which the galaxy cluster or the dark matter halo exists. And so typically when people talk about galaxy clusters, they will focus on the virialized region, but there's great advantage into extending our understanding more into the outskirts, as this tells us a lot more about the complicated physics going on, and also can teach us about cosmology as well. So in collaboration with a few people in Waterloo, we investigated a specific property of the infall region. I'm not going to go into the details, just in the interest of time. But essentially, we had a suite of 21 cosmological simulations. Each simulation was ran with a different combination of omega m and sigma 8. And so you can see the grid of simulations here. And we investigated how do properties of the infall region vary across this simulation grid. And so in this plot, each of the colors corresponds to a value, which just represents some feature of the infall region. And as you see, it varies very significantly over the simulation grid. And not only that, the degeneracy direction of this variation is orthogonal to what we expect from cluster abundances. And so, quite simply, if you can measure the value of these parameters from abundances, and also you can measure this feature of the infall region and combine these two, then that will help break this degeneracy. So very simply, this provides a kind of very promising approach to improving our information of cosmology only using cluster information, these structural properties of clusters. So how do we do this in practice in observations? Measuring the density profile of a set of galaxy clusters is not easy. The approach we take is using weak lensing. So you have a large number of background galaxies, and as their light travels past a foreground cluster, their light will be distorted by the gravitational potential. If you look at this level of distortion as a function of distance from the center of the cluster, then obviously towards the center, there'll be more distortion. Towards the outskirts, there'll be less. So that creates this lensing profile, and you can relate this to the density profile of your stacked set of galaxy clusters. And once again, we stack because we want a nice, smooth, isotropic profile. So we use weak lensing to measure the density profile of galaxy clusters. So just jumping to some results, skipping a lot of intermediate steps. So the data points on this plot correspond to the lensing profiles of galaxy clusters. I'm a member of the Unions collaboration, and Unions is currently the largest weak lensing survey in the Northern Hemisphere. It's not yet finalized, so the data is currently unmasked, and there's various other issues which are being worked on at the moment. So these results are only set to improve. And the lenses, or the galaxy clusters, are taken from the DESI Legacy Imaging Survey. So this is an imaging survey, which means photometric redshifts, which means lots of uncertainties investigated there. So I'll just jump ahead. So the main idea is you compare your data to the results from simulations, that grid of simulations we saw earlier, and you're just asking which of our cosmological simulations best fits the data. And in that way, you can constrain the values of cosmological parameters. And so these are the kind of results we get. So each one of these data points is one of the simulations and has an associated chi-squared value by comparing the profiles, the data from the profiles. And we can fit a 3D ellipse, draw 1 and 2 sigma contours. These are the results we get. So we can see the complementary degeneracy direction. The results are not yet constraining, but that's because of various issues that I talked about with the lensing and cluster catalogs. These are only set to improve, so in the future, these constraints will tighten, and this can be a very, very nice complementary and competitive probe of cosmology. So I think the prospects for this test are very good. And just to quickly summarize, ways to improve this is to use a much finer grid of cosmologies, which vary different parameters. For example, Abacus Summit. So then you would build an emulator and accurately map between the infall region and cosmology. And finally, with a spectroscopic cluster catalog, which will be possible very soon with DESI, combined with improved lensing catalogs, this is a very promising probe. Okay, thanks for your time.
So Charlie, you are getting the mass profile from weak lensing.
That's right.
But we can also look at the galaxy distribution. Is there, are the galaxies following the dark matter?
That's a good question. So yeah, the reason why we focus on weak lensing is, of course, these are dark matter only simulations. And so if you were to look at the galaxy number density profile, you would need to know the bias parameter, because galaxies are a bias ratio of dark matter. And so to have an easy comparison between our lensing observables and our simulations, that's why we choose lensing. Otherwise, yeah, you need to know the bias parameter.
Yeah, but we see the galaxies, so my question is, in the real world, are they following the dark matter?
They follow the dark matter distribution with some bias because of inspired feedback effects.
So it's just a constant factor.
Well, that's the question. It's maybe constant, maybe it varies with redshift, maybe it varies with scale. I think these are all very uncertain at the moment.
Any questions? Yes, everything was clear. Thank you so much.
Thanks.
Hello, can you hear me well?
Yes.
Yeah, perfect. So good afternoon. I am Hsiao. I'm a final year PhD graduate student at Johns Hopkins University, and I'm visiting CFA right now until this May. So thanks for giving me this opportunity to present our current study using JWST and also gravitational lensing to study some of the most distant and small-scale structure in the early universe. So I always like to show the history of the universe, my favorite plots to present. So you know that first generation of stars and galaxies are very interesting, and there remains a lot of questions, including like, are they large and bright enough to reionize the universe? Some open questions. And first stars, we haven't really seen them using current telescope. Therefore, JWST is designed. So first stars are believed to form around roughly 200 to 400 million years after the Big Bang, but we didn't detect any of them. So if we just look at the first stars and the sun, so the sun is apparently close to Earth, so it's very huge, very bright. But on the other hand, the first generation of stars are very distant. So even if they are intrinsically like several hundreds or thousands brighter, more luminous than the sun, it appears very faint. So it will be very difficult to detect individual single first star, even in the JWST era. So to be quantitatively speaking, a magnification of around 3,000 is required for JWST to detect a single length star at ratio around 10 with 60 solar mass. But you might imagine, why don't we just look at those massive, supermassive pop-3 stars? Well, it works, but also high mass stars are rare because they die very quickly compared to the low mass stars. And also the initial mass function, the high mass star and also bright pop-3 stars are already rare. Therefore, we have to be really, really lucky to ever discover one pop-3 star in the JWST era. But it's not hopeless. So star clusters, if we have a group of stars, they can actually boost the brightness to a detectable regime with a little bit help from gravitational lensing. So JWST is really doing a good job of finding this small-scale structure in the early universe. So from top to bottom, we can see from like 1,000 parsec scale, maybe like dwarf galaxies in the early universe, down to just maybe one or few tenths of parsec. So we are really reaching the star cluster scale in the early universe at redshift maybe greater than 10. So with the help of gravitational lensing, we can really see this tiny structure within the galaxies. So this one is the cosmic grapes at redshift 6. We also have the sunrise arc, the firefly sparkle, and also cosmic gems arc at redshift greater than 10. So just 400 million years after the Big Bang. So here I'm showing our amazing collaboration, our team members in Johns Hopkins University, also Space Telescope Science Institute called Cosmic Spring, and led by my advisor Danko. I actually stole this slide from his talk yesterday. So we were extremely lucky to get some of the most exciting data from JWST in a row, in 3 years in a row, including cycle 1, cycle 2, cycle 3, and we also hope to get more in cycle 4, also in the future cycles. But obviously, I don't have enough time to cover all of them, so I'll just go through that briefly and also focus on the middle one, which I was mostly working on. So this one, where we discovered the most distant lensed star called Arendelle. So this star is published in Nature, and we also got the JWST image data. So we have the SED, and then we thought based on the SED, we thought this star might consist of 2 stars actually. So an O star and another B star. Also, its host galaxy called Sunrise Arc is elongated, as you can see, and these tiny knots in between are actually young massive star clusters. So another one, Cosmic Gems Arc, led by Larry Bradley and Angela Adamo. This galaxy is at redshift greater than 10, and it's also strongly lensed. And the critical curve is actually cutting through this galaxy, so making it very highly magnified. And also we have those tiny knots in between. Those are also young massive star clusters, just down to 1 parsec, with maybe stellar metallicity smaller than 5%. But we don't have a good enough spectroscopic data for both Arendelle and also the Cosmic Gems Arc. So we're actually getting some data in cycle 3. The observation is taken right now, so we hope to get some near spec and mirror spectroscopic data to either confirm the redshift and study the metallicity, physical properties, and physical conditions in these stellar clusters, and also the interstellar medium. And the middle one is something I've been working on a lot in the past 3 years after I joined the grad school at Johns Hopkins. So this galaxy is actually discovered by my advisor Danko around a decade ago using the Hubble Space Telescope at the time. So it was the second most distant galaxy before JWST. And now we have JWST. So I'll flip back and forth here, and you can immediately tell how amazing JWST is. So why we want to study this galaxy in particular? So shout out to gravitational lensing again. Thanks to lensing, this galaxy is magnified by a factor of up to 8. So this galaxy appears to be the brightest galaxy at redshift greater than 10, even brighter than GNZ11. It's a weird galaxy, very bright. So we won't be biased to any of those other galaxies that is like weirdos, freak, Asians. So this is just a typical star-forming galaxy that is appear a lot in the local universe, that we can study such system at redshift greater than 10, just 400 million years after the Big Bang. So this galaxy, like I showed, is resolved using JWST as having 2 separate components. And you can immediately see that they have different colors, telling you they might have different physical mechanism inside. So just down to a few tenths of parsec. So we have the image data and photometry data. So I conducted the SED fitting on these 2 components. And just a quick summary of these 2 components. So JDA is the blue one. It's brighter, large, bluer, no dust, and maybe younger, and vice versa for JDB. But astronomers are never satisfied with the photometry data. So we got the spectroscopic data using the JWST near spec prism. So I'm showing this prism spectroscopic data. As you can see, there are a decent amount of emission lines, including C3, O3, and some neon lights. So we've seen some metals at redshift greater than 10. And we also got the aurora line because this galaxy is lensed, so we were able to really detect such faint line. And also we have the higher resolution grating data that we were able to spectrally resolve this O2 doublet. So both these lights can deliver electron densities and electron temperature of this galaxy that we can never see in any other galaxy greater than 10. So we were able to conduct the first direct metallicity, first ever at ratio greater than 10, without assuming any strong line calibration or assuming electron temperature, electron density, because we have the direct measurement on those parameters. So we derive around like 13% solar metallicity, so it's not like 0%, not yet the pop-free galaxy. But indeed, this galaxy, if we put down the mass metallicity relation, it kind of like follow the relation between the ratio of around 3 to 10. So we're seeing this a little bit evolution from local universe to the early universe, but we didn't really find any evidence after that. So we absolutely need more data to statistically confirm that if mass metallicity doesn't quite evolve after ratio of 3. And also this is the MIRI MRS spectroscopic data of H alpha and O3. So you might notice that after the image data, I rarely talk about the individual components in spectroscopic data. It's because we're using this slits spectroscopy to observe like multiple candidates also in a lensed field. Therefore, we had a hard time to really disentangle two clumps using this near-spec spectroscopic data. So we hoped in the future we can use IAFU to spatially resolve to really tell if one of the components may be pop-free star clusters and the other one is metal-enriched, or they may have different physical properties. So in cycle 3, GTL team will have the G395N to really study this in spatially detail. And in cycle 4, I hope there's no tech member here, but we also propose some high-resolution IFU in cycle 4, and also hope to resolve the C3 as well, and to deliver physical condition in different clumps, and also in different ionization gases that we can model to see different onion skins in different ionization zones. That's my talk today. Thank you.
One feature of POP3 stars is that above 30 solar masses, they have a very high surface temperature, 100,000 degrees, and so that would produce a lot of UV. And in principle, you can look for some bump in the spectrum at UV.
Yeah, like helium-2 1640 and helium-2 4686 are above 54 eV to ionize, and that is believed to be a smoking gun of such pop-free signature. So we didn't see that in this galaxy. So 1640 will be around like C4, between C4 and C3, but we didn't see that. But there is a pristine gas pocket in GNZ11. That one hasn't really been confirmed yet, but if the helium-2 emission from the halo is true, maybe that's something we should be looking for in the next few years. Please.
Yeah, to this note, that these GNZ11 1640, I think the proposal was approved last cycle, because I was on the TAC.
Yeah.
Okay. And so I have a technical question here. You have the Aurora line 4363.
That's right.
But the other two, they are in MIRI. How certain is the calibration, cross-calibration between MIRI and your spec in terms of flux?
Yeah. So that's for the first part, the GNZ11, yeah, they have a cycle 3 super deep observation to really confirm if the helium-2 clumps detection is correct or not, is true or not. And then for O3, yeah, we had a little bit hard time to really calibrate among the MIRI instruments and also spectral near spec. And MIRI is IAFU, so we kind of like correct for the flock lows between these slits, and also correct for IFU. And then because this system are believed to be no dust, we have the H alpha in MIRI, and we also have the H gamma and H delta in near spec. So we were able to measure the dust and then kind of like correct for that.
Yeah, but I mean, is the flux scale between Miri and near spec is well established or not, like technically? Because it's known that Miri in the long channels is degrading over time, but I'm not sure what's happening in the short channels.
Yeah, so technically, I don't know, but just based on the Balmer series and the ratio between that, we kind of like believe the calibration is true.
Can you say something about the masses? Are we talking about systems in the order of the larger globular clusters in the nearby universe, or is this for dwarf galaxy size? Or?
Yeah, so I refer them to star clusters is simply because of the scale. But for this galaxy, they have like each component have like 10 to the 7 to 10 to the 8 solar masses. So I think it's more like dwarf galaxy in the local universe in this case. And for this galaxy, for each component, they are down to like 10 to the 5, maybe 10 to the 4 to 10 to the 6 solar masses. So this one is like much smaller than next AD.
Okay, let's thank Tiger.